All right, my friends, we're going to start lecture number 4 of Arithmetic Statistics, the last and most exciting lecture because it's going to be about elliptic curves. Yay! So, first we need to fix the record one more time. If you remember, in lecture 2, somebody asked me, is this associative? Is this action associative? And I said, no, it's not. And then I thought, maybe it is. And then I convinced myself that it was, but it's not. So it is associative. It's not defined to be associative. I should have left it at, I don't know why it said the word action at all. It's supposed to be an equivalent, define an equivalence class of binary quadratic forms. But I did want to talk about them in families, sort of like the orbits. So I wanted to bring the action in. But as you know, when you're talking about actions, usually there is this thing that you should put the matrices acting inside as an inverse to make it associative. So if you actually define it as I did, it's not associative. If you put the matrix, the inverse of the matrix, then it is. And it's a nice way to see it if you write the binary quadratic forms using our alternative definition. Just write them like this with a matrix in between. Then you can see that the associativity works if you have inverses inside. Okay, so there you go. All right, so we are going to talk in this last lecture about arithmetic statistics in the world of elliptic curves. And why we're going to talk about elliptic curves is because there is a bunch of very new results or really heuristics about the arithmetic of elliptic curves that are inspired by what we've seen about the Cohen-Lenstra heuristics. So remember, we started with just counting prime numbers. We saw that at some point with prime races, that primes are 1 mod 4 and 3 mod 4 are different. Then we moved on to quadratic forms to see that they're different. In one way, they're different because they're represented by different binary quadratic forms, represent different primes. Then we started organizing our quadratic forms in families. Looking at that, we actually figure out how many classes are there for each these negative discriminants, and we connected that to class groups of quadratic fields, and we were able to make a correspondence between binary quadratic forms, classes of binary quadratic forms, and class groups, and that way prove the finiteness of the class group for imaginary quadratic fields, and also be able to work with the class group using binary quadratic forms, because we saw that the norms of ideals relate to binary quadratic forms. And then we ask ourselves, what about the real quadratic forms? How many times is there a trivial class group? And we don't know that, but we listen to Cohen and Lenstra come up with a way to think about this class group sort of in a random way and come up with heuristics of how often should a random group appear. So this same concept of a random group is going to appear a couple times today, trying to understand elliptic curves. So what's an elliptic curve? That's one. This elliptic curve is one elliptic curve that is related to some problem that's called the congruent number problem, which is a completely different talk, but a very interesting problem. So about elliptic curves, this is actually my grandfather, my academic grandfather, Serge Lang. He has a famous first line in one of his books, which is that it is possible to write endlessly on elliptic curves. This is not a threat. So I will not talk endlessly, but of course one could. There is many books on elliptic curves. My favorite books are Silverman's books are just amazing. So if you're going to take on elliptic curves, this is a good place to start. Okay, so what is an elliptic curve? And more importantly, why study elliptic curves in the first place? So we are actually interested sort of like within the field of arithmetic geometry. I would like to be able to understand the rational points on all Diophantine equations. Famously, Diophantus started in his book, the Arithmetica. He started sort of like the systematic way of finding solutions on Diophantine equations, and there are some natural questions you can ask. Can we determine all the rational integral solutions? Are there any? If there are any, are there infinitely many? And famously, also Hilbert proposed: is there a Turing machine to decide if a Diophantine equation has solutions in the integers in the first place? And it turns out no. David, Matijasevich, Putnam, Robinson, all their work together says that no, there is not such a machine that will tell you, there's no such algorithm. But however, we can talk about algorithms in certain scenarios, so we know how to determine that for linear equations, for quadratic equations. And the first time where we do not know how to solve Hilbert's 10th problem is with cubic equations. There's just, we do not have an algorithm yet to determine the rational points on cubic curves in general. Yes?
Sorry, are you saying there's provably not an algorithm? Or that we
No, we don't have one. We actually have a candidate. We have a very good candidate, which is the two descent on elliptic curves. But it's not yet an algorithm because we do not know. So the problem with cubic equations, the new problem that arises from linear and quadratic is that in cubic equations, the local to global principle starts to fail. And the way we measure the local to global principle, we'll talk about this later today, is the Tate-Shafarevich group. We do not know whether the Tate-Shafarevich group is finite. If the Tate-Shafarevich group is finite, we actually do have an algorithm to determine the rational points on an elliptic curve, which is a cubic curve that is smooth. So we do have an algorithm, so we have a good candidate. It's not an algorithm in the sense that, well, Magma has implemented, but if you put some elliptic curve with fairly large coefficients, it will never end because it's just a very time-consuming algorithm. But sort of from the computer science perspective, there should be an algorithm if the Tate-Shafarevich group is finite. Okay, so an elliptic curve then is the first case of Diophantine equations where we do not know yet how to determine rational points. So an elliptic curve is a smooth projective curve of genus 1 with at least one rational point defined over the field of definition. If we're talking about elliptic curves over fields of characteristic 0, then there is always a model of that form. We are actually interested in all the cubic equations. So this is, if you've never seen elliptic curves, if somebody has not seen elliptic curves, it seems like, okay, why are you concentrating in these very particular elliptic curves? It's because all the cubic equations of the form that are projective, genus 1, smooth, with at least one point, I can bring them to this simpler form. So why elliptic curves also is because they appear in many types of the Diophantine equations, problems, in number theory, and in other areas, in cryptography, as number theoretic applications, which we've seen with Eric scores, but in other instances, like for instance in physics, elliptic curves appear in one way or another. From our perspective, we saw, we played the other day the movie The Proof, so you saw phrase curves, how elliptic curves are connected to Fermat's last theorem. I also started the talk today with a reference to the congruent number problem, which leads to solving, finding rational points on a particular elliptic curve of that type. It turns out that the ABC conjecture is logically equivalent to specifying upper bounds on Mordell equations, which are types of a particular type of elliptic curve. Hilbert's 10th problem over a ring of integers, so Hilbert's 10th problem over Z was proved to be non-solvable by the people I mentioned before. But if you change the ring of integers, that is not solved in all rings of integers. So it turns out that if you want to solve it for a ring of integers of a number field, then it can be shown to be undecidable if SHA actually is finite over that field. So there is many important problems that are just go back and connected to elliptic curves themselves. Okay, so hopefully that is enough for you. I have a much more basic interest in elliptic curves, which is, I think they're just really cool. So actually, we'll talk about the rank. That's what excites me the most, trying to find elliptic curves with high rank. So as you probably know, there is an addition on elliptic curve. You can make the set of rational points into an abelian group. If you have 2 points on an elliptic curve, you can draw a line through P and Q, find a third point of intersection. If P and Q are rational, because you're intersecting a cubic with a linear equation, you're going to find that the third point is rational. And we define, actually, we define the addition, so P plus Q plus R is 0. And that tells you then that P plus Q should be somewhere over here. Okay, and there is some other point going to infinity. There is the point at infinity works in projective coordinates. There is one more point, and the point at infinity works as the 0 of the group. Okay, as you can probably see from my T-shirt, I really miss writing on blackboards, so I brought a blackboard with me. So you can also do multiplication by 2, for instance, or addition of a point to itself on an elliptic curve. This is the elliptic curve that we talked about at the beginning related to the congruent number problem, y squared equals x cubed minus 25x. And for instance, that's related to the congruent number problem in that, so Fibonacci found a right triangle of area 5, and that's those points there, that corresponds to a triangle of that area. And you can find more triangles with that area by doubling that point. So to double a point, what you do is you trace a tangent line at P, and then you can find new points on the elliptic curve. So that new point gives you a new triangle with area 5. All right. But more importantly, Poincaré conjectured, or I think in the writing at least of Castles, it's more than conjecture. He assumed this to be true, that the points on an elliptic curve is finitely generated abelian group. And then Mordell proved it over Q, and they generalized this to abelian varieties over any number field. Nowadays, there is even a farther generalization, what's called the Mordell-Weil-Neuron theorem, which tells you that actually, what is it? Any group that is finitely generated over its prime field, for an abelian variety over one of those fields, the group of points will be finitely generated. So you can do a little bit better to include all global fields. So for instance, over Fp adjoint T, so over a function field, over a finite field, there is also a finite generation of the Mordell-Weil group. So, in particular, using the structure theorem of finitely generated abelian groups, that tells you that the points over an elliptic curve over F will be happy with to understand what's happening over Q. There is a decomposition where there is a finite torsion subgroup and an infinite part. But there is only a finite number of generators of the infinite part, which we call the rank, that R of E over F. Okay, so for instance, this elliptic curve has a point of order 6. That point P has a point of order 6. This elliptic curve has a point of order 5. We'll see some other examples and pretty pictures along the way. More examples of things that can happen for a Mordell-Weil group. So you can have an elliptic curve that has no rational points whatsoever, except the point at infinity that is always there. You can have an elliptic curve that has only finitely many points. For instance, that one only has 6 points. You can have an elliptic curve that has no points of finite order, but has points of infinite order. That elliptic curve has infinite points, infinitely many points, and is all generated by one point. And you can have a mix. You can have torsion and infinite part. So what we would like to know is what possibilities are there for the Mordell-Weil group as you vary over all the elliptic curves, say, over a fixed field. Again, this is an open problem even for Q. So whenever I write F, just think of Q, or perhaps a function field, like in the setting of Christel's talks. Okay, so what happens there? Well, as I said, we don't know what happens with the full Mordell-Weil group, but if I fix my field F and I try to figure out what are the possible torsion subgroups over that field F, then actually you can get some mileage and try to classify all the possible torsion subgroups that happen. And this has been done in a number of cases. Myself and my students have actually done a lot of work on classifying torsion subgroups over different fields and in different settings. So, for instance, over the rational numbers, that is already a quite challenging theorem. So Barry Mazur famously proved this classification in 1977. This was conjectured by Levi, then sort of forgotten and reconjectured by Ogg, that the list of possible torsion subgroups should be these, I believe, 15 groups. That these should be all of them, and Mazur completed the classification. So that we know. And we know more. We know what happens over quadratic fields, and now we know what happens over cubic fields, and that's it. We have some partial information over quartic, quintic, sextic. We have some partial answers, but not full answers. So here's, for instance, an elliptic curve. That big point here, that point has order 12 on that elliptic curve, and this is the Cremona label of the elliptic curve. So from the point of arithmetic statistics, what we would like to know, I've told you the classification of what torsion subgroups can happen, but from the point of arithmetic statistics, we would like to know, okay, you told me that, but like how likely is it that I'll find an elliptic curve like the one you just gave me? Is this happening all the time? Like if I pick random coefficients, will I see these torsion subgroups? So we would like to count how often this happens. So we're going to consider elliptic curves we're going to put them in order. How do you order them? Well, there's a number of ways to do it, and it is actually, the jury is still out of like how should we count elliptic curves. And spoiler alert, I think we're all counting them the wrong way so far, but we'll see if that changes at some point in the future. So here is an elliptic curve, and what we do is, as I said, you can always find over Q, you can find a model like this. This is a short Weierstrass model or Weierstrass model of an elliptic curve with A and B integers, and I'm going to write them so that this number, which is called the discriminant of the elliptic curve, is just minimal in that isomorphism class. That means that we don't want a common fourth and sixth power dividing A and B, because that makes an isomorphism of these models. So these are a family that contains exactly one copy of each isomorphism class of elliptic curves over Q. Okay? And I want to line them up in a line and then start doing statistics about them. So we're going to define what's called the naive height. Is just the max, just about the size of the coefficients. So you see that there is a weight on the coefficients. So we actually pick the height of the elliptic curve is sort of based on these formula for the discriminant. So an elliptic curve, the height will be 4a cubed or 27b squared, whatever is largest. Okay, and then I'm going to call ex all the elliptic curves up to height x, and then I'm going to try to do sort of like we would like to do is do some sort of like prime number theorem of elliptic curves, and that is done. That's actually a theorem of Brumer, tells you sort of like the prime number theorem, how many elliptic curves are there up to x. What I would really like to know is how many elliptic curves are there of each rank, for instance. Okay? But we're going to do torsion first. So this actually has been done, and fairly recently. This was not known, and Rob Heron and Andrew Snowden, the good Snowden, I should add, they actually proved that the following. So if G is one of the groups in Mazur's list, then let ng of x, all those elliptic curves in my family that have up to height x the torsion group is isomorphic to G. How many of those are there? Well, they give a count, and they find that the limit of the log of that quantity over log of x is 1 over d of g. But you would like to say that ng of x is asymptotic to x to that power of 1 over d of g. They don't get quite that far. They prove that actually for when g is 0, or further 2, or further 3, they prove a better estimate than this. But in general, what they can prove is this estimate of log over log. Okay, and they give a complete list of these d of g's. I just wrote a few of them for the cyclic prime ones here. And actually, every d of a non-trivial torsion subgroup is bigger than the trivial subgroup. So what that means is that there is by far more elliptic curves with trivial subgroup. So if you do all the elliptic curves and just compare how many are there, then there is a density of 100% of elliptic curves have torsion that is trivial. Okay, 100% of all elliptic curves. So there is infinitely many of each kind, and there is in fact they come in one parameter families. So I can give you precisely a description of all of them with one torsion subgroup, but there are very thin families among all the elliptic curves. Okay, so yes, question.
Sorry if you already said this, but are all of these rational numbers?
Yes. In fact, the only one that is not rational is d of 0. So the d of g's are all natural numbers. Yep. So if you go to their paper, which is easily accessible in the archive, then you can see they have a very nice little table with all the values, and then you can see what's sort of like the relative density is. It's a very nice paper. It ought to have been done long ago, but it wasn't. So I was very surprised when I saw this, and it's just one of the favorite papers. Okay, so we know torsion. We know how often it should happen. We know how to parameterize all the elliptic curves with a given torsion subgroup. So the torsion subgroup is the poster child for what an arithmetic family should be. We know everything there is to be about over Q. So what about the rank? Nothing. We don't know what values can happen. We don't know how to write the families of elliptic curves with a given rank. And we don't know densities of how many there should be. We don't even have a heuristic or an asymptotic that we even agree on conjecturally of how many there should be of each rank. So it's a wide world, how would you say? It's like the Wild West of conjectures right now, that we don't know anything really with much certainty. So it's a very exciting time to be alive. Okay. So how do we want to study ranks over Q? I'm going to pick families of elliptic curves, perhaps all the elliptic curves, and I want to know what the family of ranks looks like, or in some particular subfamilies. People are also interested in what's called a quadratic twist family. So you fix an elliptic curve, you fix your A and B, and then you twist it, and what happens is, well, there's some twisting happening at the color representation side, sort of like that justifies the term twisting. But over the elliptic curve, what you do is just change A by A d squared and B by B d cubed. And that's a new family of elliptic curves. They're not isomorphic over Q. They become isomorphic over a quadratic extension. But that family over Q has different ranks. What are the ranks like when you go through a family like that? Nobody knows. Okay. So that's the open problem. What values can the rank take? And can the rank be arbitrarily large, or is it uniformly bounded over Q? And there's been zigzag of opinions. First, people had no opinion. Then people thought that it was bounded. Then there were some results over function fields that the rank is unbounded. And because, like what Christelle was saying, like the comparisons between Q and function field, they said, oh, is it true over function field that the ranks are unbounded? Then it should be unbounded over Q. And we thought it was unbounded for a while. And then as of recent, there's a couple of different heuristics that point to the ranks being bounded, uniformly bounded. So what you believe is still like, it's up in the air. You can read papers and try to convince yourself one way or the other. So what do we know? The evidence is actually very thin for the ranks to be arbitrarily large. However, the largest rank we know, so Elkies found this elliptic curve of rank 28, or at least 28. I think if we assume BSD or some other standard conjectures, you can prove that the rank is exactly 28. But so it's not even provably 28 at this point. Then this is such an example. This is the highest rank we know. So there are points of infinite order. There are 28 of them. Here's points 1 through 3, 4 through 11, 12 through 28. By the way, I don't know if you've noticed, they're all integers, integer coefficients. It's such an amazing thing that there's so many integer points on an elliptic curve, on a cubic curve. The curve itself is amazing. So you can actually go for current rank records. There's a website, which is the website that got me into this business, where Andre Dugela keeps track of. I just kicked the button. That doesn't do anything bad. So he is keeping track of all the historical records of like what ranks have been known when, and actually by torsion families. So the elliptic curve that Elkies found, that elliptic curve has trivial torsion. But what if we want Z-mod 2 torsion and high rank? Then there is a different, there is a very different record there, I think, also by Elkies. But you change torsion subgroup, and then the ranks change. I was just fascinated by this list, and I'm so excited that I'm going to Zagreb later in June, and I'm going to meet Dugela, and I'm going to take a picture with him, and it's going to be awesome. Okay, so the rank. How many elliptic curves are there of each rank? As I said, Brumer showed that there's some sort of like prime number theorem for elliptic curves up to height x. And I believe it's like they're asymptotic to x to the 5/6. Okay, so what about a prime number theorem type for elliptic curves with a given rank? So you fix the rank R, then define all the elliptic curves up to height x with rank R, and define an elliptic curve counting function, pi r of x, and then we want to know how many elements are in there up to each height. We would like an asymptotic for that. We don't have it. But there are some conjectures about what happens with the rank. Most famously is the 50-50 conjecture of Goldfeld and Katz, Katz-Sarnak, that is as follows, that if you fix a global field K, so think Q or a function field over a finite field, asymptotically, 50% of elliptic curves over K have rank 0, and 50% have rank 1. Okay, this is also called, or in support of this or related to this, is the minimalist conjecture of people like Maser that said, like, well, the only reason for the rank the only constraint on the rank is the root number of the functional equation. According to BSD, the root number of the functional equation tells you if the rank is going to be even or odd. So if the root number is -1, it cannot be even, so it has to be odd. And then it has to be the minimal number possible. So it has to be, there is 50% of all root numbers are even, so 50% of the ranks should be 0, 50% of the root numbers are -1, so 50% of the ranks should be odd, and the lowest number, it should be 1. And that's it. And so they conjecture that this is true overall, that in the limit, 50% of the curves are rank 0, 50% are rank 1. When you look at the data, it looks very different from this. But we are allegedly only able to look at very tiny amounts of data in principle so far. And so, moreover, the average rank, so if you do the sum of all ranks up to height x divided by the number of elliptic curves up to height x, that should go to 1/2 as x goes to infinity. Okay? It was formulated, I don't have the year. I'm not sure, 70s or something. What do we have now? Nowadays, as of very recently, Balakrishnan, so our fourth co-organizer, Ho, Kaplan, Spicer, Stein, and Wiegand, they released a database of 238 million elliptic curves. So that goes up to height 2.7, 10 to the 10. So that's a lot of elliptic curves. But remember that the naive height was defined as the max of a cube of a square. So if you take the cube root of that number, that height, it's not that big. It says that the coefficients are like 10 to the 4 or something, up to 10 to the 4. So up to 10,000? So the coefficients go up to 10,000? That doesn't seem like a lot once you actually think about it. So there's just 238 million elliptic curves, as I said. It still feels like, like if you were trying to look at prime density of primes and you were counting up to 10. You would get a very different impression of how many primes are there overall. Okay, so you have to be careful with the data. And in fact, we knew that the data was lying to us in that the average rank, we were having very many doubts by looking at the data compared to the conjecture of Goldfeld, like the 50-50 conjecture or the 1/2 conjecture. So this is the average rank graph for the data of the database that I mentioned, the BHK-SSW database, Balakrishnan, Ho, Kaplan, Spicer, Stein, and Wiegand. So prior to their database, the data we had ended here. So not only the average rank was not going to have, it was like shooting up to the sky. So we were very worried that what the heck is going on with the data, that it does not indicate at all that the average rank is going to have at all. It's actually increasing. So it was nice to see with their data, it was the first time we saw a hump and then start to go down. And you see it's trickling down, 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 down. It's not even at 0.9 yet. The last value is 0.9019 because we're far from 0.5. This, by the way, in terms of results, this is the best we have. So Skinner proved this bound on the left, and Bhargava and Shankar proved this bound on the right. These two sort of like mild-looking inequalities are amazing results. So under here goes essentially everything we know about the current state of the art of results on Birch and Srinivasan Dyer conjectures. Okay, goes into proving this. And here goes basically the full force of Bhargava's geometry of numbers, as he calls it, or amazing theory, as the rest of us calls it, of the geometry of numbers. So the full force of what we know, sort of like the arithmetic statistics, or also what people call Bhargavology, goes into this inequality. So these are two amazing results, but that's what we know, that the average rank will be sandwiched between those two numbers at least. We expect it will go to 1/2. So it's very hard to get better estimates than that. All right.
Can you do any better assuming BSD?
No, I don't think so. Because so the reason why we can actually prove this unconditionally, this side here, using what we know about BSD, is that, as I said, most of the weight of the average rank will come from elliptic curves of rank 0 and 1. So if you know how many of those are there, that already is the largest contribution to the average rank. So if you can prove there's a ton of elliptic curves of rank 0, there's a ton of elliptic curves of rank 1, where the BSD is known, then you can sort of prove something about the average rank using those results. So if you knew BSD for rank 2 and 3, maybe you could increase a couple of decimal places in there. I'm not sure you could do a lot better. I might be wrong. I should say that word is on the street that there may be a proof of the Goldfeld conjecture coming out soon. Yes?
That's just a lot less than a second. Is this the limit as x goes to infinity?
I'm sorry. That yes, that is correct. That the average rank, the overall rank, the average rank overall should be between those two values. Yes, obviously we see that the average rank is higher here for these values of x. So yes, that is true. Good point. All right. What else? In my own work, actually, I have done what I believe is the first heuristic approximation of what these functions should be, the average rank. So I developed a probabilistic model for ranks of elliptic curves that it spits out a lot of information, at least up to rank 5. As I said, because of the average rank, the first 0, 1, 2 ranks contribute the most for the average rank. I can actually give you a somewhat approximate value of what the average rank should be. So this is a very conjectural heuristical model for the graph of the average rank. And according to my model, the red line would be what the model predicts. And you can see that the error, this is actually pretty zoomed in, the error in here is about this much, which is about 0.0003% or something. Or I'm sorry, it's about this much, which is about 0.0523% of the value. So it's getting pretty close, or it matches the data pretty well. And using that, as I said, it's highly heuristical and conjectural. I can at least give some idea of what the average rank should be as you increase the height. So remember that this is the largest database we have, goes up to height about 10 to the 10. So I expect that if you want to see 0.5, then you're going to get somewhere in like 10 to the 50. If you want to really get close to a half, we're going to have to go to about 10 to the 200 in height. And that's just inconceivable at this time. Okay, so in general, how do we compute ranks? We use summer groups. I'm not going to have time to define what a summer group is, but if you go back in time and you go to CTNT 2016, then you could take my lectures then, and I spend a lot of time talking about summer groups then. Or there are videos of it, and you don't have to build a time machine. So you can watch the videos if you want to know a little bit more about summer groups, or pick up a book. Okay, so what is a summer group? It's a homologically defined group. I don't know if homologically is a word, so I wrote homological, defined group, such that the Mordell-Weil group, in particular the weak Mordell-Weil group, the weak Mordell-Weil group is a quotient of E mod 2, say, or E mod n, so that a weak Mordell-Weil group, I can embed it into it. Why would I do such a thing? Well, because there are good news. So the summer group is something that is homological, therefore a little bit scary to think about. But once you actually go down into the details, it's very computable. It only requires local computations. It only takes finitely many primes of local computations. So it's actually very nice to work with. And two summer groups are very easily computable and decidable what points are in the summer group and what not. In particular, you can realize all the elements of the two summer group, for instance, as quartics, and then you're trying to find whether those quartics are locally solvable everywhere, and therefore just building the summer group. So it's very easy to work with. What are the bad news? You were waiting for them. Here they come. The bad news is SHA. So the quotient of Selmer by the weak Mordell-Weil group, that's called SHA, and SHA is it's a mess. So it's very hard to compute because it measures the failure of these spaces here, these quartics, those that I know that are everywhere locally solvable, so there are real points and there are points over QP everywhere. Now I need to know, is there a Q point? If these were quadratics, then the whole Minkowski theory, Minkowski would kick in and would tell me, yes, there is global points. Over cubics and beyond doesn't happen, and then I have to find my way out of this mess. So those elements of SHA can be interpreted as the quartics in here that are everywhere locally solvable, but not globally solvable. And it, as I said, is very hard to compute. We do have some means to compute it, which is higher descents in where these might disappear when you do, instead of a 2-week Mordell-Weil group, you do a 4-week Mordell-Weil group or an 8-week Mordell-Weil group, and try to figure out what's happening up above. Okay, so what else? So we are interested in the Selmer groups because of, by the way, this is an F2 vector space. So this is an F2 vector space. So we're just talking about F2 vector spaces, and this embeds in here. So the dimension of this is less than the dimension of this. And there is also one piece that comes from here is the 2 torsion. So if you define the dimension of this minus the dimension of where the 2 torsion lands, that's called the Selmer rank, or the 2 Selmer rank. And what we have is an inequality that the rank of the elliptic curve is less or equal to the Selmer rank. So just by computing Selmer ranks, you at least have a bound for the rank of the elliptic curve that sometimes is tight because you already know some rational points, and then you can prove these are all of them. If there is no Shah, you are done. If there is Shah, then good luck. Okay. So what do we know about the Selmer group, about the size of the Selmer group? This was actually what Bhargava and Shankar used for that inequality that I said before. It came out of this work where they proved that the average size of the 2 Selmer group in the family of all the elliptic curves over Q is 3. They also proved that the average size of the 3 Selmer group in the family of elliptic curves is 4. And then they conjecture that actually the conjecture is that the average size of the P Selmer group is P plus 1. And in fact, there's a conjecture that the Selmer group, the average size of the N Selmer group is the sum of the divisors of N. So you see that P, the divisors are 1 and P, so that's why you get P plus 1. Okay? But in any case, we know that the average size of the Selmer group, of the 2 Selmer group, is 3, so it's typically very small. Okay? It is just an amazing result that was not expected that we could get our hands on things like this. Okay, so what about how many elliptic curves are there of each Selmer rank? I don't know the rank, but maybe I can model what happens with each Selmer rank. We don't know that either. However, there's a conjecture of Poonen and Raines that says exactly how many you should expect of each Selmer rank, which, remember, is a bound for the rank. So the conjecture is that the limit, so the average over all the family is actually given by a very precise formula. And it tells you that, for instance, there should be about 20% of elliptic curves have Selmer rank 0, therefore rank 0. 41% should have Selmer rank 1, and then 27%, and so on and so forth. Okay? So it gives you already some stratification of how many Selmer ranks you should find of each order. Okay? Which, as I said, those are bounds for the ranks. It is known that there are elliptic curves of arbitrarily large Selmer rank. That's not hard to prove. But it is also known there are elliptic curves with arbitrarily large Shah. So that's the bad news. Okay, so you can do that. We've done 2 descents, which is embed the weak Mordell-Weil group into the 2 Selmer. You can do P descents, and there are people that have worked out the equations to do 3 descents and 5 descents and other types of descents. So one question you might ask is that, okay, what I need to know is the difference. If I know the size of this, then what I need to know is the size of this. And if you've been awake for the last 3 lectures, or at least the last one, you might ask, is Shah a random group? And it would be a very good question, and you get a lot of papers out of it if you had thought about it about 15 years ago, but now it's done. Okay, so the answer is no, you were wrong. You were paying attention, but this is not, if you paid attention, we said last time, the class groups of quadratic imaginary fields, we said it's a random group, but we also said, no, you're wrong. Why? Genus theory tells me there's something about the 2 part there are constraints. There's a constraint here too. It's been known for a while that the Shah has a bilinear pairing that is non-degenerate and alternating. That's called the Castle state pairing that forces, for instance, this number of elements in SHA to be a square. Okay, so it cannot be just any group. It has to have this property. That's sometimes a group with a bilinear pairing like this is called a symplectic abelian group. Okay, so it has to be symplectic. I like saying the word symplectic, so I might say it often. Okay, so what if, okay, then let's assume that it's a random abelian group, but it's symplectic. So assume that it's a random finite abelian group, G, with a symplectic structure. So there is a non-degenerate alternating bilinear pairing beta. Then is it random, but with that property? And it looks like it. So Delaunay, what he did in 2001 is say, okay, let's assume it's a random finite abelian group, and I'm going to put a weight of 1 over the size of the automorphism group. That should be no stranger to you, except that not just any automorphism. I have a group structure together with my group, so it has to be automorphisms that respect the group structure, which is the bilinear pairing. So automorphism groups that preserve that bilinear pairing, that's the weight I'm going to put on. And it turns out to look very nice with the data we have. So he obtained Cohen-Lenstra type heuristics for the probability of each isomorphism type of SHA. There's a picture of him. So that looked very promising with the data that we have, which is not a lot, at least not a lot when he came up with the heuristics, but now we have more data that seem to work well with what he proposes. So for instance, so these conjectures now come in families that actually tell you what SHA should be if you know their rank. So if you fix the rank R equals 0, for instance, then it comes up with some conjectures of what SHA should be. If the rank is 1, there is some other set of conjectures, and so on. So you know a little bit more precise. So for instance, it's easy to state when the rank is 0, then the probability that SHA is divisible by P, by a prime P, is given by this function. This should be a P. So, for instance, the probability that SHA is divisible by 2 is 58%, or 36% divisible by 3, and 20% divisible by 5, and so on. Okay? And this is in the limit. So you have to take all the elliptic curves together. In the whole family, this should be the probabilities, or at least according to Cohen-Lenstra heuristic type. Okay? Bhargava, Kane, Lenstra, Punian, and Raines did remember what Friedman and Washington did? Do you remember what they did? Cohen and Lenstra came up with, why don't we do 1 over the size of the automorphism group as a weight? And Friedman and Washington went and said, okay, what about if we model random groups as generators modulo relations? Come up with a matrix, put a measure in the matrix, and see if we get those statistics. Well, guess what? Somebody did this for elliptic curves too. So Bhargava, Kane, Lenstra, Punian, and Raines did the following. So if you have the exact sequence of Selmer and Shah, you can do an exact sequence for P to the n, and in fact, you can do it for QP modulo ZP and get a sequence of ZP modules. And now the question is this, by the way, this is supposed to be finite, so it's a quotient of ZP modules that gives you a finite group. And so what they do is build a sequence of ZP modules, so just come up with a matrix that is going to give me, like before, like in the Friedman and Washington setting, that this quotient is going to model this. But of course, like we did last time, sometimes this might not be finite. So that's why I'm taking the torsion part of that. You asked me, is the matrix a full rank? Well, here, let's forget about the full rank. I'm just going to take matrices and then take the torsion of the core rank of my matrix. Okay? So they draw the comparison between SHA and these type of kernels. Okay? So you can actually do like we said before, we're interested in curves with a given rank. So you can fix the rank R. That in the model is that the kernel has rank R. And also, we don't want any matrix that is n by n. We want matrices that will have we want this to end up being symplectic, right? If you put just any matrix in here, this will not be symplectic. But if you put a if you put an alternating matrix, then it turns out that this quotient is naturally symplectic. Okay? So you do that. You do the distribution of alternating matrices, and then what they prove is that when n goes to infinity, the limit distribution coincides with the Cohen-Lenstra distribution that comes from Delaney's model. Okay? So very cool. Just give some weight to the heuristics of Delaney on the distribution of Shah. That's interesting. And now, in the last minus 1 minute, I'll say that so Park, Poon, and Voigt and Wood have done the following, building on that model of these ZP matrices. They've done the following model, which is they're trying to model elliptic curves of a given height h. And for that, they're choosing a height h. They're choosing a dimension uniformly at random in some interval that depends on h. Then they're choosing an alternating matrix of relations, but this time with integer coefficients, not ZP. Remember, we started with a random model, said like, okay, let's do ZP modulo relations, and then we said, like, but we want a P group. Well, they are trying to do that, but model all of the rank and all of SHA at the same time, not just the P part. So they are looking at matrices with integer coefficients that are alternating. So there is a symplectic structure that the cancel state pairing still holds. And the matrix, the coefficients now, the integer coefficients, so there is a measure on it, they are bounded. And then what they are doing is the co-kernel of the matrix models SHA, and the rank of the kernel models the rank. So they're modeling both things at the same time. Remember in the previous slides, the rank was fixed and we were trying to get statistics on SHA. They're modeling both things at the same time. And then they get things like this. So out of their model, some of the consequences are that they get heuristic for the elliptic curves of rank at least R grow like this. And then once you go up to 21, all of a sudden this becomes just 0. And then they expect that all but finitely many elliptic curves satisfy that the rank is less or equal to 21. Now that's curious because we do have already examples of ranks beyond 21, but it might be that Elke's example is one out of finitely many such examples that are there of elliptic curves of rank higher than 21. But as I said, the jury is still out of what of these models is correct. So this is it. It's a very exciting time to be looking at ranks of elliptic curves. And I think since I'm out of time, I'll stop there. Thank you.